I think we can start. Good afternoon, good morning to our participants. It's my honor today to welcome you all to our webinar on the role of AI in revolutionizing autonomous vehicles by Professor Daniela Ross. Professor Daniela Ross is a board member of MBZUAI, and she is also Andrew and Erna Viterbi Professor of Electrical Engineering and Computer Science, and Director of the Computer Science and Artificial Intelligence Lab, CSAIL at MIT. She serves as Director of the Toyota CSAIL Joint Research Center. Dr. Ross's research interests are in AI, robotics, and mobile computing. She is a class of 2002 MacArthur Fellow, a Fellow of ACM, AAAI, and IEEE, and a member of National Academy of Engineering and American Academy of Arts and Sciences. She is also the recipient of 2017 Engelberger Robotics Award from the Robotics Industries Association. Dr. Ross earned her PhD in computer science from Cornell University. I remember my first encounter with Professor Danielle, where she emphasized the role of women in AI, and being Dr. Ross, she is a role model, and please join me in welcoming her to our webinar of today. Professor Danielle.
Thank you so much for this warm welcome and introduction. I'm going to share my slides, my screen. I hope you can see it. Let me know otherwise. It's really a great joy and honor to be here, and especially to do this seminar in a way that is enabled by our work. We are here together in this virtual mode because of work that the computer science and the AI community has done to enable telepresence. And if you think about it, today telepresence enables us to come together. It enables students to meet with tutors and teachers. It enables doctors to treat patients, and all this when you're thousands of miles away. Today, we also have robots that help with packing of factory floors. We have network sensors that enable monitoring of facilities. We have 3D printing that creates customized goods. We are surrounded by such a world of opportunities, and these opportunities will only get larger as we start to imagine what we can do with advances in AI and robotics. So just picture a world where routine tasks are taken off your plate. Fresh produce might just show up on your doorsteps, delivered by drones. Garbage bins might take themselves out, and smart infrastructure might support automated pickup of your garbage. And AI assistants, whether embodied or not, will act as guardian angels, providing advice to ensure that we maximize and optimize our lives to live well and work effectively. That is an extraordinary possibility. Now, this possibility is enabled by progress in 3 connected fields. One is robotics, which puts computing in motion, giving machines the ability to move. The other one is artificial intelligence, which gives machines the ability to see, to hear, to reason, and communicate like humans. And then we have machine learning, and machine learning aims to learn from and make predictions on data. And in the future, these technologies have the potential to reduce and eliminate car accidents, to better monitor, diagnose, and treat disease, to keep your information private and safe, to deliver education to everyone. In other words, to allow human workers to focus on big picture tasks like critical thinking and strategy, while machines can take on routine work. And this progress is impacting many industries, but some are more advanced than others. So financial services and high-tech communication are leading the charge, but other services like building, travel, even healthcare are falling behind. Now, the technologies that are enabling this kind of progress are primarily rooted in data and are primarily about machine learning. And 2 key approaches to machine learning are called supervised and unsupervised learning. In supervised learning, we use positive labeled examples and negative labeled examples, for example, instances of cars and not cars, so that when new data is presented to the system that is trained using these positive and negative examples, the system can label correctly that data. For example, the system can predict that the blue picture or the blue item in the picture is a car. Now, in unsupervised learning, the algorithm does not use any labels in order to figure out how to identify objects. But what the algorithms do is they cluster the data and they look at internal features to determine natural groupings in the data, such as cars and animals in this example. So these are the two main approaches to machine learning. And all the fields that have data can benefit from these approaches. I want to show you medicine, because medicine is a really great example. Machines today can look at more radiology scans in a day than a radiologist will see an entire lifetime. And a new AI-based approach was tasked with reviewing images of lymph node cells to diagnose cancer. Now, on its own, the system made 3.5% error as compared to the human's error at, so the system made 7.5% error as compared to the human's error at 3.5%. But when both the AI system and the pathologist reviewed the data, the error improved by 80%. It went down to 0.5%, which is extraordinary. And so today, these technologies are deployed in the world's most advanced cancer treatments in the world. But imagine a future where everyone has access to these systems. An overworked doctor who may not have time to keep up with the latest and greatest clinical trials will be able to offer their patients the most cutting-edge diagnosis and treatment options with support from these technologies. Now, an important aspect of working with AI in medicine is the privacy of the data. So people can contribute their data for the greater good, but if they do so, will the insurance companies respond in negative ways? Will there be negative consequences to their private sharing of data? We've been very interested in the question of how can we fold privacy in this big loop of handling data, whether it's healthcare or it's from any other field. And to show you what we can do, I want to give you an example as a motivation. So this is a data set of breast tumors. In green, we have the benign tumors. In red, we have the malignant tumors. And right now, one way of thinking about a new kind of tumor that gets queried against the system to see whether this tumor is malignant or benign is done through an algorithm called k-nearest neighbors, where the idea is as follows. The queried tumor is placed in the space of the other tumors. It is compared against the existing data, and it is allocated the type of the k-nearest data points to it in that space. And so an interesting question is, can we do this encrypted? Can we do this in a way that does not reveal any information about the queried tumor to the database, and it does not reveal any information from the database to the query or to the people posing the queries? So it turns out that we have new technologies that allow us to do exactly that using encrypted computation. And this is absolutely extraordinary because it is a new method that allows us to do computation without decrypting data. It is called homomorphic encryption. And so the idea for our example is that the client would encrypt the query, send it to the database. The database would compute the class of the query without decrypting it, send from the server to the client the result, and then the client will decrypt the class to understand what the result is. If you think about it, this is extraordinary. This kind of technique could solve so many problems around privacy. And the fact that we can do this in the context of AI is even extraordinary. Now, homomorphic encryption is not a magic bullet because there are some significant challenges with how we can compute in this model. But what you should remember from this talk is that it is possible to do this kind of classification in machine learning in a way that does not reveal any privacy aspects, any details from the client nor from the server. So that's a great advancement. The other advancement I want to tell you about is natural language processing, because this has been exploding in efficacy. And so I want to look at natural language processing in the context of law, but we can take education, we can take any field that needs access to data. And I want to highlight that already word processing, internet, and email have revolutionized how lawyers go about their work. The next wave of technologies, natural language understanding, promises an equally profound change, because now with natural language processing systems, with systems that can read entire libraries of cases, lawyers will be able to predict what a judge might do based on existing evidence. And so again, this is really quite extraordinary. And over the summer, we had since the summer, we have a new natural language processing system called GPT-3. It's a new model that has been trained on every single text that was written by humanity. 45 terabytes of data went into training the system, which now has 175 billion parameters. And so it was trained using a lot of energy, a lot of petaflops and days, as you can see in this chart. It was trained using electricity that amounted to about $4.6 million. So very expensive. But now that we have done this, what can we do with this? Well, the system can carry on a natural conversation. And so, for instance, here is a sample text from interacting with the system. What is your favorite animal? My favorite animal is a dog. Why? The system says, because dogs are loyal and friendly. What are 2 reasons that a dog might be in a bad mood? 2 reasons that a dog might be in a bad mood are if it is hungry or if it is host. It's really quite extraordinary to see the kind of natural language, the kind of meaningful language that the system generates. And in fact, the advent of this kind of natural language processing model is causing an entire revolution in the chatbot industry. For example, I just want to show you an example from a startup that recently IPO'd. In fact, during the summer, it IPO'd with great success in the United States. It's called Lemonade. And Lemonade is processing insurance, both signing up and getting insurance claims. It's processing it with a language interface that is so intuitive, so simple. My students report that they use it. And so we are expecting a revolution in how natural language is used for interaction with systems. This will impact a lot of industries. Now, working together, machines and people can do so much. Humans can augment and amplify many aspects of our work. For example, we can have businesses use AI to understand what customers are saying on social media in real time. Systems can automatically alert businesses on supply chain issues. We can have instantaneous translation systems. You can have a system that translates from English to Arabic instantaneously with the same error rate as human translators. There are so many opportunities. And these business opportunities are enabled by a lot of advancement in AI, machine learning, and robotics. But some of today's greatest successes are due to a technique called deep learning. And I wanted to explain how it works so that you understand how the applications we're going to talk about work. Now, deep learning uses data, usually millions of hand-labeled examples, to determine the weights that correspond to a node in a network, so that when the network is used with new input, it will classify that input correctly. For example, the human has labeled the previous image as beach, palm tree, and ocean. And now when the human sees this image, it can say it's a beach. And so this process works in two steps. First, the pixels of the image have to be grouped according to the object they belong to. And then those objects have to be labeled. And so computers can very naturally and automatically group the pixels together in objects, as you can see in this picture. But it is really humans working in call-like center conditions who end up manually labeling the data. So this is a very labor-intensive activity and a significant challenge to machine learning. There are other challenges to machine learning. So deep learning has enabled a lot of new applications, but there are also limitations. For instance, if you look at these two pictures of dogs, these two pictures should look quite the same to you, but they're in fact slightly different. The second picture was obtained from the first picture by injecting a little bit of noise, which you see here. And this noise is sufficient to trip a machine learning system that correctly labels the first picture as a dog to label the second picture as an ostrich. So that's another big challenge for machine learning systems. Robustness, the idea that the system can be tricked to make mistakes so easily is a big problem. Now, the other point about machine learning I wanted to tell you is that the reasoning level of these systems is fairly impoverished. So in this video, you see an 18-month-old that is watching a scene for the very first time ever. And look at what he does. He is able to figure out what the adult wants to do and how to help the adult. Currently, there are no AI systems that do this level of reasoning. In fact, most AI systems work by pattern matching. So if I tell you that a machine learning system will translate what I say into Arabic, the words may come across correctly, but the system will not really understand what I'm talking about. So there are many challenges with today's AI solutions. Some are about data availability, meaning that we need massive data sets that have to be manually labeled. Some are about data quality, meaning that bad data means bad performance in the system. And so we really need data that has no bias in it and that has the right scope that includes all the corner cases we need to train our systems. Also, the computational requirements can be very high, as you could see in the GPT-3 example. Finally, we have systems that are not able to explain how it is that they do their reasoning, that are brittle and that don't do extensive reasoning, that are shallow learners. And so, so given this, question is, what can we do? Well, actually, we have also a lot of opportunities, and the opportunities are primarily fueled by AI, by the AI community's great work to address these challenges and to enable many opportunities that are around the corner. We have many opportunities to rethink the models used for machine learning. We have many opportunities for supporting humans and machines working together, where machines do what they're best at, meaning computing very fast, finding patterns in huge, vast seas of data, whereas humans can make the final decision, can do the reasoning. So I want to show you some ideas for how these opportunities are being enabled. And so first, I want to address data quality, because data quality is very important to train any machine learning system, and especially safety critical systems like robots, where you cannot have mistakes. So I'm sure you have heard about the problems with machine learning systems that are used for face recognition and come up with very biased responses. And so what can we do here? Well, using a new technique, we can actually, in some sense, almost fix the data set to debias it and have a more representative set of images. And here's how we can do it. The first step is to learn the latent structure. That means the underlying parameters of a data set. And the second step then is to estimate the distribution of the parameters. And from this, we can observe what is prevalent and what is rare in the data. And next, we can adaptively resample the data and create a more fair, debiased data set. So we have techniques that allow us now to take bad data and turn it into better data. We have also techniques to tackle the size of networks, the efficiency of networks, and the interpretation or the ability of these networks to understand what is happening inside this engine. And to illustrate these new models, I want to start I want to use an example in autonomous vehicles. And I want to start by explaining to you that the traditional solution of an autonomous driving pipeline is to break up the problem and solve many sub-problems, and to do so in a sequential way. So using sensors on the AV, we can answer what is happening around the AV, and then using a special set of detectors, we can figure out where the obstacles are, where the people are, where the other cars are. Then using another set of techniques for the localization problem, we can find where we are relative to the obstacles. Then we can figure out where the vehicle should go and actuate. And the challenge with this pipeline is that each one of these modules has to be developed independently and has to be parameterized and hand-coded for every type of road situation there is. If you're driving on the left side of the road or on the right side of the road, you're driving on country roads, you're driving on roads with lane markings, you're driving at night, you're driving during the day. All of these conditions have to be folded into the pipeline, and this can get very cumbersome. Now, in our lab, we've asked the question of whether we can replace the middle part of this pipeline and go directly from raw images to actuation by learning from humans how to drive, by literally observing how a human steers and figuring out how to do that, because then we would have an underlying representation that could, in some sense, capture all the situations that otherwise would have to be hand-coded. So it turns out we have done this successfully. And here is an example of how an autonomous vehicle is doing a first autonomous drive in an environment that it has never seen before. Now, this vehicle uses 3 cameras, one pointed to the left, one pointed forward, one pointed to the right. It also uses a topological map. And using information from from GPS that is very that is not robust, that is sparse, but using the map and using the vehicle's ability to detect intersections, the vehicle can localize, the vehicle can steer, and the vehicle can handle a road situation has never been trained for. This vehicle was trained around MIT in an urban setting on roads with markings. Here's the vehicle driving on roads without markings. The vehicle is able to recognize where it is. It's able to recognize where it has, how it has reached the desired goal. Now let's look a little bit under the hood. This is what our end-to-end driving system does. And so what you see in this video is the map of the vehicle and its path in red in the lower right corner. In the middle, the yellow, blue, and green dots represent the firing of the neurons in the end-to-end deep learning network that is driving the system. And the convolutional layers that you see in the middle are for processing images. The network is for deciding what to do. And then in the lower left corner, you see the attention map. That means where are the neurons looking in order to determine what to do next. So first of all, I'd like to call your attention to the reasoning part of the network, which consists of over 100,000 neurons. And if you look at how these networks fire, it's very difficult to understand any patterns. Then I'd like to call your attention to the attention map, which also is very noisy. And you can see that the focus of the network is all over the place. So what can we do to make this better? Well, we have used inspiration from biology. We have used inspiration from the neural structure that was mapped for earthworms. And it turns out that the earthworms have only 300 neurons. And on 300 neurons, the earthworms are able to move in the world, to find food, to find a mate, to live a good life. And so that's really extraordinary. The neural networks used by robotics applications and by other types of applications use hundreds of thousands of neurons. So what's the difference? Well, biologists found that the nodes, the neurons of the earthworm are driven by differential equations, whereas in the classical model for neural networks, we use a very simple thresholding function, a step function. So we have explored the idea of creating neural networks that replace the step function with a differential equation. And if we do that, we can replace the end-to-end driving system, the reasoning engine you have seen in the previous movie. We can replace that with 19 nodes. So 19 nodes accomplish the same as over 100,000 nodes. And one benefit of that is that, in fact, now we can look at the firing pattern of the 19 nodes, and we can actually visualize what is happening in the system. So, in fact, here in the middle of this video, you see how the neurons function, and you can see how those firings are associated with different behaviors. So let's watch a little bit. So we can't keep track of 100,000 nodes, but it's really quite intuitive to look at our 19 nodes and to see how the vehicle steers. Moreover, we can associate individual nodes with specific behaviors of the vehicle that are much higher level than reasoning about pixels or about XY coordinates. And now look at the attention map. The attention map is also so much cleaner. Our solution is focused on the sides of the road and on the horizon, which makes sense intuitively. That's where we want to look in order to decide what to do next. And so an interesting result is that using a different model for neuronal computation, we are now able to represent much more compact networks. And here is the difference between the networks. I actually don't have time to go into the mathematical details, and I'm not even sure you are very interested in that, but we can map very large networks that consist of hundreds of thousands of nodes into much smaller networks that we can then visualize better. Now, these networks still need to be trained. And the question is how to train them. Because if you train the network using a driver that is able to stay on the road and do the right thing, you end up with a very boring data set that does not contain crashes, that does not contain erratic driving. So this data set is not going to help the system respond to surprises that may lead to accidents. We have developed a new strategy for training networks that works as follows. We take one very high definition data set, so we have the vehicle drive on one trajectory. And then in simulation, we generate lots and lots of different trajectories that look equally high definition to the network. And we do so in simulation by using computer vision techniques. So here's how this might work. This is the original data. You can see the single drive that was used to train the network. And now in simulation, we can train a lot of realistic drives, and you can see the simulated trajectories and the steering, and you can see what the world looks like from the point of view of the new trajectory. And using this approach, we can generate lots of different types of driving. We can generate crashes. We can generate a much richer data set that will improve what we can do with driving. So we have accomplished a lot to enable autonomous driving on the roads. And you know what's really exciting? What's really exciting is that the solutions that we have developed in the context of vehicles that drive on the road can also be deployed on other types of mobile devices. And our most recent work shows how we can deploy the same solutions on autonomous boats. And so here is our rowboat, that's what we call it. It's an autonomous robotic boat that navigates on the canals of Amsterdam and the rivers of Cambridge using the same sensor suite, using the same pipeline that we have developed for autonomous vehicles. And this robot can promises to really revolutionize how we do operations, especially if we have the ability to move some of the human activities to water. That would be really extraordinary. So I should tell you, we built this robot at 4 scales. We built a quarter scale vehicle that we experimented with in the context of fleets of robotic boats. We built a half scale vehicle where we experimented with adding weights to the vehicle and removing the weight from the vehicle. And we are in the process of building a full scale boat that will shuttle tourists in Amsterdam. And so, but in addition to moving people and goods with this robotic boat, which you see conceptualized in this image, we have so many other ideas for what you can do with systems like this. So because of the geometry of this boat, we can imagine creating platforms that would allow people to gather. Maybe on these platforms, you can have floating food markets. You can have pop-up gathering places. We can imagine using these platforms just on time to help deliver people from robotic boats to the shore. We can imagine adding robotic arms to these platforms to help dispose of garbage. And then we can imagine infrastructure, autonomous infrastructure that will move all the trash collection operations to the water. So how realistic are some of these ideas? Well, here you see the quarter scale boats that navigate to create new platforms, to create new structures. So you can think of these as autonomous modules, and you could see them aggregate in different shapes. You can also see them navigate either autonomously or as a collective. I think there is so much opportunity in this space. So I've shown you some advancements in autonomous driving and some applications in autonomous navigation with boats. Question is, where are autonomous vehicles today? Now, the way to think about the status of autonomous vehicles is in terms of their capabilities. And the capabilities are can be classified in terms of how fast is the vehicle moving, how complex is the environment where the vehicle is moving, and how complex are the interactions between the vehicle and the environment. And what I can tell you is that today we have robust solutions at the origin of the system of coordinates. We have robust solutions for vehicles that move slowly in environments where you have a low interaction complexity. So what does that mean? Well, here you can see a vehicle we have been deploying in Singapore since 2012. So this is really quite mature technology. But if it snows, which you can't experience in Abu Dhabi, but if there is a big rain, or if there is a desert storm, and the sensors end up bouncing off of particles like sand grains or snowflakes, the perception systems of these vehicles do not work, and we need to think about how to handle those cases, and we're working on that. Also, if you have a complexity of interactions, and here you see a video I took in Bangalore about a year and a half ago, just look at how difficult this road situation is. We have cars, we have people, we have motorbikes, we even have animals sleeping in the road. These types of interactions are very difficult to handle by today's systems. So ultimately, we want to get to robotaxi, but in order to get there, we have to improve the technology. We have to tackle the environments with more complexity in the interactions. We also have to tackle much more challenging environments. And we're doing this. We're developing research in these areas, but we're not quite ready for deployment in prime time. And so to show you what it is that we are doing in these spaces, I want to remind you what the classical autonomous driving pipeline is. The first blocks in the pipeline are about perception, working with sensors, determining where are the obstacles, determining where I am relative to the obstacles. And so we are thinking a lot about perception. We're thinking a lot about how today's autonomous driving solutions that are being tested in companies use very high definition maps. These are maps that provide us with centimeter accuracy for every object in the world. And these maps take a huge amount of space. So for instance, if you were to take a high definition map for San Francisco, it would take 4 terabytes of data to store. And as compared to that, the entire planet, all the road network, the entire road network on the Earth, it requires only 40 gigabytes of data storage to store. So think about how difficult it is to extend an autonomous vehicle solution that relies on high definition maps. So in our group, we are looking at whether we can use AI, we can use other methods to not rely on high definition maps. And in fact, here you can see one of our solutions. And this solution is what we call self-driving for country roads. It's a solution where we simply eliminate the high definition maps and we replace them with topological maps with essentially the same kind of maps that humans use when they drive. And here you see some results that are captured in a video using a system that does not use prior three-dimensional maps. This vehicle uses real-time detection of the road. In other words, it finds what are the drivable parts of the road, and then using that, it estimates how to steer and how to move in the world next. So the good news is that with a solution like this, we can take an autonomous vehicle and we can place it in an area that has not been pre-mapped. We can place it on a country road where we don't have lane markings. We can place it in the desert. We can place it in the woods. We can place it in lots of other places. Let's see, that's the movie again. What do we have here? We also, let me move on. So we have developed the solution. The solution is enabled by AI technology. We have also began to think about what are some of the critical aspects of computation that deal with interactions. And here, part of the problem is that computer vision still makes mistakes. And so if you have a classical pipeline, that requires that we identify every object in the system, and we classify that object with a type, the system will have a hard time labeling people. It has a hard time with people moving in clusters. It sometimes mistakes these high tabletops for people, and it has a hard time identifying people when they push or pull things around. So instead of doing that, we have developed an idea that essentially says, let's not label the individuals in the scene. Let us think about how they move rather than who they are or what they are. And let us create these force fields we call risk level sets that tell the vehicle where are the no drive zones and where are the drive zones. And we can take this idea and we can map this idea for driving on roadways, but we can also take this idea and apply it to driving in pedestrian areas. And so here you can see an autonomous wheelchair that uses this idea to navigate a very crowded hallway at MIT. And what you see on the right-hand side in green are the no drive zones computed with these risk level sets. And I should tell you, I'm going to play the video again. I should tell you that this experiment happened just at the end of a class period, and the vehicle has no idea that all these people will come in and out of the classroom. But just look at how agile the vehicle is and how it's able to find a path even though the environment is fairly challenging. Now, another aspect of dealing with challenging interactions is exemplified by some of the experiments, some of the early experiments the car companies, the autonomous car companies have done. So in the summer of 2018, Waymo deployed a fleet of vehicles in a town in Arizona, and allowed those vehicles to interact with human-driven vehicles. And what happened was that the robot cars entered intersections at the same time as human-driven cars and didn't know what to do. They became paralyzed. And this is because they did not understand, nor could they coordinate with humans. So it turns out that when we drive, we have kind of silent inter-driver communication. I notice if I want to make an unprotected left-hand turn and you slow down, I know that you are doing that, and I'm able to speed up. But if you speed up, I know that it will be dangerous to enter the intersection. Well, the vehicles could not understand what the human intent was, and so as a result, the humans were very annoyed by the fleet of vehicles that blocked the intersections. And so this kind of situation can be mapped mathematically onto what we call social dilemmas. And the social dilemma is a situation in which the collective interests are at odds with private interests. And so, for instance, in this case, what should happen? In the top row of this chart, you see a situation where the black car slows down to allow the blue car to make a left turn. In the bottom row, you see a situation where the black car accelerates and the blue car has to wait until the black car passes in order to make that left turn. We as humans can observe the situation on the road and know whether we are in the top situation or the bottom situation. But autonomous vehicles are not able to reason through these situations as of now. So what can we do? Can we do anything to handle this? Well, it turns out that we can use a metric from the social psychology literature called social value orientation. And social value orientation is measured in terms of the reward to self versus the reward to others in a social situation. And it turns out that that can be mapped onto an angle, which can be estimated. So here's how it works. Let's say you have $100 and you are asked to share the $100 with someone. So one thing you can do is you can keep $0 and give away $100. That's an altruistic behavior measured by 90 degrees. You can do 50-50. This is called a pro-social behavior, and it corresponds to pi over 4 or 45 degrees. Or you can keep everything, and this is an egotistic behavior. It turns out that we can take this notion, this idea of measuring reward to self versus reward to others, and we can figure out whether the driving situation is a pro-social or altruistic or egotistic situation. And this can be mapped onto a solution for autonomous driving that uses reinforcement learning to figure out in which situation we are. And then we can take the solution and we call it autonomous driving with SVO, with social value orientation. We can take the solution and we can put it on robot cars that are now able to understand the language of the humans on the road. They are able to understand whether the humans are egotistic drivers, pro-social, or altruistic drivers. And by doing that, we can improve the safety and the efficiency of autonomous driving systems. We can also enable autonomous driving systems where humans and robot cars, human-driven cars and robot-driven cars can coexist. And here is some real-time simulation that is done with a real car situation. It's called the NGSIM data set. And so we've been able to measure exactly how our machine learning solution that uses the SVO and also uses game theoretic reasoning is able to improve safety. So this is exciting because it really opens the way to a world where robot-driven cars can begin to coexist with human-driven cars, can begin to understand each other's language. Now, I want to talk about transportation impacts of this kind of thing. And so when we think about transportation, we also have to think about fleet management. We have to think about who is driving when and where. And in the United States, we have a lot of cities where people don't drive, where it's mostly taxi companies who provide the fleet management. And I wanted to share with you a result from one of my projects. So we're using AI techniques. We have developed a new algorithm for matching supply and demand. This algorithm can be applied to any situation, but we've applied it to optimizing the rides that are performed by taxis in New York City, where on average 400,000 requests a day are supported by 14,000 taxis. It turns out that with our system, we can reduce the number of vehicles to about 3,000. And we can do, and if we do so, we meet 98% of the transportation demand by introducing a guaranteed trip delay of no more than 3 minutes. So just imagine the crowded New York City without 10,000 vehicles that roam around continuously. Of course, this raises some ethics issues and some issues around the responsible use of computation, because the natural question is, are we going to put 10,000 taxi drivers out of a job? But if we reason about this situation from multiple points of view, we see that in fact the same solution could be implemented by giving the taxi drivers shorter shifts, because there's the same amount of money that flows through the system. So with shorter shifts, we can generate the same revenue, we can keep the same taxi drivers, the taxi companies make the same profit, but now we have better traffic and lower pollution in the city. And so AI can really enable a lot of other possibilities around general transportation. Now, before I end, I just want to show you a few other examples where AI and robotics can make a big difference on our lives. And so one area of healthcare I've been very excited about is the possibility of doing surgeries with robotic surgeons. I call them mini surgeons because they're tiny. They are the same size of a medicine pill. And the case study I've looked at is removing a button battery that people actually swallow regularly. There's thousands of people who swallow batteries in the United States and even more around the world. Now, the batteries are dangerous because they create a hole in the tissue very fast, within an hour. And so usually you have to have a surgery. But now, what if you create these tiny robotic pills that can be encapsulated in water, that can be swallowed, and when they get to the stomach, the ice melts, the robot deploys, and now an MRI-like machine can be used to control the robot. So here is an example in a simulated stomach. You can see the robotic pill. The robotic pill has a tiny magnet in it. This magnet is used to identify the location of the pill, also to drive it to the battery where the robotic pill can pull out the battery to remove it. And now a second robotic pill can come. This pill is now infused with medicine. The robot can be driven to the location of the wound, where it can patch the wound and deliver medicine. There are so many possibilities for transformation in the health industry. The other one I wanted to show you is a robotic device that we developed in March when the pandemic started. And within about a month, our student created an open source robotic emergency ventilation system that is taking, and the robot is consists of the green hands you see in this video. The cyan object is a lung, and what you see in between the hands is called an ambu bag. It's a manual ventilation system that is inexpensive and broadly available. So our students created a template for how to take a manual ventilation system and turn it into a mechanical ventilation system that could be built inexpensively using local parts like motors that are used for windshield wipers. And this the system has been picked up by many countries around the world. There was even a team of women in Afghanistan who took our designs and turned them into local solutions. So very exciting to see our technology saving the world or contributing to improving the world. So I just wanted to leave you with a view of where all this stuff is going. And so so imagine a future. Imagine a future where when you wake up, you have your personal robot assistant that figures out the optimal time to wake you up and helps you organize your outfit and collects all the other items that you might need for the day. Then you walk to, what have I just done? I've just, sorry, I've accidentally changed my, my screen. So, okay, where is my? I've accidentally shifted to a different screen. So then you, when you walk to the store, you might even have new interfaces that will project your picture on with the latest fashions on the store window. And when you go inside the store, a personal assistant might let you figure out how to customize the latest fashions onto your body. And maybe we would even have clothing that has embedded sensors and computational fibers that allow you to change what you look like, perhaps to match your friends. And maybe at work, you would have an intelligent boardroom where sensors can monitor your comfort level, and gestures can be used to pull up and modify diagrams that are being used to design a new car, perhaps a flying car. And at home, perhaps you would have bikes, robotic bikes that grow training wheels on demand, and you have robots that deliver packages, and you have robots that help with gardening, and you even have these garbage bins that can take themselves out because they are robots. And after a good day, when it's time for a bedtime story, you might be enabled to actually enter the story and interact with the characters. All of these are possibilities that are enabled by our advancements in machines, by our advancements in creating better brains for machines, creating better bodies for machines, and creating more intuitive user interactions between people and machines. And so this is really extraordinary because the computational advancements in AI and in robotics will create a world where we will be much more empowered to use machines in more powerful ways, to use machines that support us with cognitive tasks and with physical tasks. And with this, I would like to pause and see if there are any questions.
That was so great, Professor Daniela. Thank you very much. Really, we enjoyed it. And yes, we have questions. I'd like to have the first question to you was from one of the participants that says that deep learning algorithms require a large amount of data to learn properly. However, human can learn some tasks from a small amount of data, such as object recognition. What is required to make deep learning algorithms learn robustly from a small amount of data on some tasks?
Yeah, so that's a really great question. We have to think about this at multiple levels. So first, I should say that there is a very active machine learning community that's working in few-shot learning, and there are a lot of other researches that are focused on active learning, on reducing the actual data set. So my own perspective is that we should really think hard about what are good examples for learning. Do you really need 2,000 examples of a cat to learn what a cat is? Well, in a few-shot learning or active learning approach, the idea is to intuitively examine the pictures of a cat and figure out what are some of the features that are prevalent in all the examples that represent the same concept, and then perhaps create a synthetic example that captures all those features and train the machine learning engine on that example. In fact, my colleague Josh Tannenbaum has shown a very effective system where he used the handwriting data set, and he showed that there are thousands of examples of digits, of numbers 0 to 9 in this data set. But he showed that he could synthesize exactly one example for 0, exactly one example for 1, exactly one example for 2, that trains the system effectively to learn what those concepts are. So I think that using a kind of a compression technique, my favorite is corsets. We've used corsets a lot, if you know what those are. So using a kind of a compression technique coupled with this kind of synthetic image creation, much like what I showed you in the context of driving, we can train much better. If you think about the driving example I have shown you, we generated one high definition data set, and then in simulation, automatically we created a lot of variations on that data set. So that was inexpensive because we were able to use computer vision to do all the labeling and all the processing that went along with that. So people are trying various techniques that reduce the number of or the amount of effort required by humans. But of course, you have to think about data in many different contexts. It's one thing to talk about vision data where we have a lot of processing tools, and it's a completely different thing to talk about, let's say, financial transactions, time series that are associated with other types of data where we do not have the vast amount of tools that is available in computer vision.
Great, thank you. I would like to thank you, Professor Ross, for the great talk that you have given us and how the future autonomous vehicles and self-driving cars can change our lives to be better and more safe and efficient. For the audience, there is a survey to rate our session, and I would encourage every one of you to please participate in that. I promise it is very short. It wouldn't take from you even a minute time. The survey is on the screen, and please help us to rate this. Again, thank you very much, Professor Ross, and very much appreciating your talk. Thank you.
Thank you for having me.
Thank you.
Have a good evening.
Good evening to you. Happy voting.